In today's podcast, we're going to talk about dot structures, how to draw those. And basically what Lewis dot structures are going to do is allow us to show how different atoms are bonded to each other in a molecule. So these are going to be for covalent compounds. And they'll show you how the atoms are arranged, and also then we'll use them to predict geometry of molecules, so figuring out what shape, what things look like in three-dimensional space. So real quick, I just want to remind you about how many valence electrons different elements have and what the trend is on the periodic table. So the first column, the alkaline metals, always end in S1, so they have one valence electron. The second column here has two, they always end in S2. Then you'll remember that all of the transition metals always have two because you'll get that S2 and then it goes back down into a lower energy level for the d electrons. This column right here ends in S2P1, so there's three valence electrons, and then 4, 5, 6, 7, and 8. Now for Lewis dot structures of compounds, we're really only going to be working with covalent compounds, so we're really going to be just working with the nonmetals, everything to the left of the staircase or to the right of the staircase line. So when you're drawing a dot structure, there's some basic steps that you'll always go through. In order to draw the dot structure, first of all, you need to know how many valence electrons you have. So the example we're going to work through is chlorine, Cl2, which is a diatomic element. We'll talk more about that in this unit. But so if we want to know what Cl2 looks like, first of all, we have to figure out how many electrons it has. Well, if we go back and look at that trend real quickly, chlorine is in the halogen column, and there are 7 valence electrons with each chlorine atom. And we have 2 chlorines in this molecule, so the valence electrons will be 2 times 7. So I need 14 electrons in the dot structure. So to draw a dot structure, I'm going to write the symbols next to each other, because they're going to be bonded to each other, obviously. And then I'm going to draw a line to represent a shared pair of electrons. You can also write it like this. And maybe this is easier for the first time. So these two electrons, or these two atoms, are covalently bonded. They're sharing a pair of electrons, and we show that by drawing a pair between them. So that's 2 electrons taken care of. Then what I need to do is distribute whatever's left, the other 12 electrons, around each of the atoms until everything has a stable octet. Okay, so this already has 2, 4, 6, 8, 10, 12, 14. Okay, so I've distributed all of the electrons, and you'll notice that we have 8 electrons around this chlorine and 8 around this chlorine. So the way that these obtain a stable octet is by sharing those 2 electrons, so that each chlorine has 8. You can also write it with the line here, and then you would have the dots around the other sides. Okay, so hopefully you remember from when we did dot structures of elements that we always had the 4 sides of the symbol, and then and we distribute the pairs that way. One note, if you have a hydrogen, it only needs 2 electrons to be stable, because remember, it's in that first row. So when it becomes like a noble gas, it's going to become like helium. All right, let's look at a couple more. Here's another little tip to keep in mind when you're trying to figure out how a dot structure goes together. When you're looking at the formula for a compound, then usually the first element in the compound goes in the center for the structure, unless it's hydrogen or something else that can only make one bond, because generally hydrogen is just looking to find one more electron, so it would just make one bond, and that's true with the halogens as well. So they won't be in the center, and we'll look at some examples like that. So here's CF4. So remember, our first step is always to figure out how many electrons we have. So if we go and look at our periodic table, carbon It's right here, has 4 valence electrons, and fluorine is right here, it has 7. So if we add all that up, we've got 4 for carbon, plus 4 times 7, that's 28. So 28 plus 4 means we have 32 electrons that we're going to need to use in this dot structure. So we start by joining everything with single bonds. And I'm just going to draw the line. Remember, that line represents 2 electrons. So that's 4 electrons, 6, 8. Okay. And then I need to distribute the rest. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Okay, now we can see that each fluorine has 8 electrons around it, because remember this line represents a shared pair, and the carbon also has 8 electrons around it. Okay, now the dot structure for water, H2O. Obviously the hydrogen's not going to go in the center because it only makes one bond, and so it can't have these other things around it. So we're going to put the oxygen in the center and then bond the hydrogens to the oxygen. Okay, but we didn't count how many electrons we have total. So oxygen, if you go look at the periodic table, is 2 away from the noble gases, so it has 6 valence electrons. And oxygen, oxygen has 6. Each hydrogen has 1. So we have 2 times 1, so total of 8 valence electrons. All right, now remember with hydrogens, they only need 2 electrons to be stable, to have that stable octet. It's not really an octet for hydrogen, but it's stable. So by sharing with the oxygen, this hydrogen has 2 and this hydrogen has 2. So those hydrogens are already happy. Now we need to figure out the oxygen. So far we've distributed 4 electrons. We have 8. So put 2 more here, that makes 6, and 2 more here, that makes 8. So that's the dot structure for water. So a couple more things that you'll need to think about. One is if you've distributed all the electrons, but you still don't have a stable octet, then you need to add things like double or triple bonds. So obviously a double bond would be when atoms share 2 pairs of electrons. A triple bond is when they share 3 pairs of electrons. So let's look at oxygen. Each oxygen atom has 6 valence electrons. So for this dot structure, we would have 12 electrons to deal with. So we're going to join everything with a single bond. So that's 2 electrons. Then we distribute everything else in pairs. So 2, 4, 6, 8, 10, and 12. So we've distributed all of them. This oxygen has 8 electrons around it, but this oxygen only has 6. That's a signal to us that we need to add a double bond because we're 1 pair short. And so the way we do that is we would move the 1 pair, so get rid of that pair right there, and put in a double bond here instead. So now each oxygen is sharing these 4 electrons here. So we've got 4, 6, 8 around this oxygen, and 4, 6, 8 around this oxygen. So this is how we can achieve a stable octet for both oxygens in this molecule. Carbon dioxide is another example of a molecule where you need to include double bonds. Carbon is in the column that has 4 valence electrons. Oxygen, has 6. So I've got 12 plus 4, I have 18 electrons to distribute in the structure. So remember, the first thing in the formula usually goes in the center, and then we put everything else around it. So 2 oxygens bonded to the carbon. So that's 4 electrons we've taken care of so far, 2, 4. And I'm just going to start distributing them around. 6, 8, 10, 12, 14, 16, 18. So right now, I just realized that I made an adding mistake, didn't I? This isn't right. 12 plus 4 is usually 16. Okay, that makes a little more sense. So now I need to erase a couple of those electrons because we only have 16. Okay, that's better. That makes more sense to me now. Okay, so I have 2, 4 in the bonds, 6, 8, 10, 12, 14, 16. This oxygen right now looks pretty happy. It has 2, 4, 6, 8, but the carbon only has 2, 4, 6, and this oxygen only has 2, 4, 6. So there are 2 pairs of electrons missing. In other words, there's this carbon would need 2 more and this oxygen would need 2 more. That means we need 2 double bonds. So what we're going to do here is move a couple of pairs. So I'm going to move this pair right here. I'm going to move this pair right here. And I'm going to put in double bonds instead. So now this oxygen has 2, 4, 6, 8. This carbon has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. So now everything has a stable octet. One more thing that can also happen is sometimes we need to draw dot structures for polyatomic ions. And in that case, we need to add or remove electrons to deal with the charge. And then I'll show you how we draw it at the end with square brackets. So SO4, sulfur and oxygen are both in the same column. So they each have 6 valence electrons. So total, we have 5 atoms that have 6 valence electrons. And then this 2 minus charge means that there are 2 extra electrons in the structure that they would have picked up in reacting and forming. So the total here is 30 plus 2, 32 valence electrons. So always the first element goes in the center, unless it's a hydrogen or halogen. And then we join everything around with single bonds, so SO4, so 4 oxygens. And that's 2, 4, 6, 8 electrons. We need 32. So 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So that distribution was pretty easy. Everybody clearly has 8 valence electrons now. Now, when it's a polyatomic ion, we need to have square brackets around it to show that it's an ion and not a molecule. So we put square brackets around it, and then we write the charge outside to indicate that it has 2 extra electrons in its structure. All right, just another one to see how these work. So this one's called carbonate. Carbon has 4 valence electrons. We know that oxygen has 6, and we have 3 of those. And then because we have a 2 minus charge, that means it has 2 extra electrons. So we've got 4 plus 18 is 22, plus 2 more is 24 valence electrons to put in this structure. So we put carbon in the center. We join 3 oxygens with single bonds. So that's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24. Now, if you're not careful, you might think, oh, good, I'm done. The oxygens all have 8 around them. But this carbon only has 2, 4, 6 valence electrons. So we've distributed all of them, but we don't have a stable octet around the carbon. That means we need to add 1 double bond. So I'm going to just move 1 pair, and it doesn't actually matter which oxygen I take them off of, and change that into a double bond. So now I've got 8 around this oxygen. I've got 2, 4, 6, 8 around this one. 2, 4, 6, 8 around this one. And the carbon now has 8 around it. So this is the correct structure for carbonate, except since it's a polyatomic ion, I need the square brackets and the charge outside. So that takes us to the end of this podcast. We'll practice some more in class. Make sure that you have clear notes about what the steps are to making a dot structure, and we'll continue to work on this some more.